There we go. Now we are. Don't know why that keeps happening. That's a good turnout for a first session back. Good to see you all. And some new names at least. Great, let's just wait one more minute so everyone is in the room and the beeping outside the door stops. Right, so we already have 2 volunteers going forward, by the way. So Michelle was busy reading books over the summer, and he volunteered to present 2 books, and Lilith also volunteered to present a paper next week. Is that right, Lilith? Yes, cool. So we already have a stretch sorted for Neuroccino. That is looking great. A countdown now. So welcome to Neuroccino, our weekly journal club. We're just back from the summer break, and there was a lot of exciting news in the science world that came out, so we're ready to review. Just a quick repeat, the rules of the game. Everyone is welcome to present, just volunteer yourself like those 2 just did. And then come and present the paper to the best of your knowledge, and we discuss it to the best of our knowledge. And it should be fun and short. You don't have to prepare a PowerPoint presentation. It's really just pull up the paper and you're good to go. Now, I thought I'd make a start today. So let me first share the link. We're not going to review a classical paper, but I thought this was an interesting feature in Nature just at the end of last week. Titled Europe Spent 600 million to recreate the human brain in a computer. How did it go? So for those of you who don't know, this is about the HBP, the Human Brain Project, and that is coming to an end this September, end of September, so this month. And it was a 10-year project, one of the biggest funded by the European Commission. So it's only fair they try to wrap up and see what came out of it. Let me share the screen so you can see the paper as well. Share screen. Here you go. I'm gonna zoom in so you can see it better. Okay, does that work for you? Thumbs up? Yes, cool. Okay. So, as I already said, the title online was Europe Spent 600 million to recreate the human brain in a computer. How did it go? Well, the answer is so-so. There was thousands of papers that have been published, but arguably, depending on who you speak to, no conceptual breakthrough, which you would expect for a 10-year program. And that is due to the fragmented and the disjointed efforts that are in part down to leadership, but we're going to come to that. But so overall, the project did not achieve its goal of stimulating the whole human brain. And I thought it's a good review, for being aware of these big projects, but also seeing that it's not the end of the world if there's a Nature feature about your project saying that you did not achieve your goals. But let's go through it. So the actual title is a bit more calmed down. Scientists aim to recreate the brain in a computer. How did it go? And what they actually achieved to produce and put out was a 3D map of around 200 cerebral cortex and deeper brain structures, and indexed 6 previously unknown brain region in the prefrontal cortex, more specifically in the sulcus, that contribute to memory, language, attention, and music processing. Now, the legacy of this project is called eBrains, and we're going to come to that in a minute. But basically, it's a digital infrastructure for collaboration, because obviously they are aware of the fragmentation and the disjointed efforts. And the idea is really to work together and combine it. Just as a point of reference, this is obviously not the only big data brain project. Most of you are at least aware of the counterpart in the US, the Human Connectome project, that will run until 2026. Then Japan has its own program for 15 years. China started a program in 2021, and Australia and South Korea are in the 7th year. So you can see this is a common effort across the, well, not common, but not common in a sense that people work together, but common in a sense that everyone wants to have that kind of data. As I said, the key aim of this project was to develop the tools and the infrastructure that are required to better understand the functioning and the organization of the brain and its diseases. So why did they not achieve what they set out to do? You can see that here. And that is in part due to mismanagement, especially in the early years. So it started in 2013. In 2014, so just 1 year into it, they already decided to take cognitive neurosciences out, which led to 18 labs leading the consortium, and 150 scientists signed a protest letter to the European Commission, to which the European Commission then replied and reviewed the program and implemented or requested some changes. First one being to revise the scientific objectives, because understanding the brain is a bit too broad to actually have impactful outputs. They also changed the organizational structure of the HBP from having 3 people in charge as the board to a larger board. And then between 2016 and 2020, more managerial changes took effect. But the problem that the HBP was faced with is that it left scientists a bit wary of the project. Now, arguably, cognitive neurosciences was brought back into it, but is not the strong suit at the moment, that's for sure. Now, the way it was organized is that they had 6 specialized platforms. And the idea was that they start separately, but then as time progresses, they start converging towards the common goal. And these specialized platforms included things like brain stimulation, high performance analysis and computing, and neurorobotics. So again, you can see that the focus for cognitive neuroscience is not the strongest. Now, management aside, what is the scientific output and contribution of the HBP? And one of the things that they created was a Google Maps for the human brain. So those are the 3D maps that are openly available. And I told you it's the legacy of it called eBrains. And I just opened up the viewer for you. So this is what eBrains looks like. Everyone can sign in and make an account, contribute data, use data. And it's really a infrastructure that is scattered all around Germany with the hubs for the computing and the analysis networks. But this is really supposed to be a collaborative effort in the end. And I fired up the brain viewer if it's working. Here you go. So you can load different atlases. I just opened the multi-level human atlas. You can open different templates. Again, I just stuck with the default for today, the ICBM. And then you can select your kind of parcellation. So we have the fiber architecture, obviously the one that I've played around with. But you also have functional nodes. You have, of course, the cytoarchitecture, cortical layers, and the isocortex. Now, for those of you who know, if I click on deep fiber bundles, you can already see one of the limitations from our perspective. And that is great that the white matter is there, but obviously this looks like a classical DTI algorithm. where you miss big chunks of the white matter. So if we look at the corpus callosum coming out, the corticospinal tract coming up, we see they should be crossing and, whoops, where's the camera here? They should be crossing and actually passing through each other, but they don't, they stop, and actually there's a gap in the map. So this is anatomically not entirely accurate, but what is actually quite beautiful is if you change for the superficial fibers or the U-shaped fibers, you have a pretty good coverage of the whole brain. And this is from the HCP, so the Human Connectome Project. That's another thing they try to integrate with other databases that are available. Now, one of the things that I thought was a bit of a shame, let me see if I can go back. So if you click on the structures, you should be getting information, but it's not as detailed. This one obviously worked now, but when I had the white matter and I clicked on it, the information was quite limited for the white matter. So this was one of the things where I see a limitation. But other than that, you really have a Google Maps for the brain, so you can start from far away the surface and then really zoom into the cellular and molecular details of the brain. So that means that the atlas is multi-level, and they also try to partner up with the Allen Atlas to get the gene expression for their cortical area. So you can even look into that. As I said, they used those setups to identify 6 new brain areas. And for those of you who are interested, here is the paper in cortex, and it's actually in the inferior frontal sulcus where they separated the 6 areas. Now, the biggest outcome, I would say, next to the eBrains platform is the algorithms that come out. So everyone can contribute to algorithm. They also provide some. So you have a nice scaffold to model the brain using various brain imaging, including microscopy images. Now, another big part of the HBP that is part of the greatest hits is the so-called digital twins. Have you heard of digital twins? No. Okay. So digital twins are mathematical representations of a person's brain that merge scans from an individual with a model. And the whole thing is done virtually, obviously. So you can kind of think of it like making an avatar of you online. And then before any treatments are applied to you, they're applied to your digital twin first to see if, given your individual circumstances, this is likely to have a positive effect on your system or your brain. So that's roughly the idea behind digital twins, and a lot of people are working on digital twins. Obviously, the HBP is coming from the brain side of it, but also went to a vernissage last week and met an electrical engineer, and they also use digital twins trying to model the brain. So there's bound to be a convergence at some point. And within the HBP, they use digital twins for epilepsy and Parkinson's already with some success. So as I said, the early stages was marked by fragmentation, but the new leadership is very aware of that, and they're trying to overcome this by sharing data, coming up with standard data formats, building the platform eBrains for collaboration. 2 more things before I'm happy to open the discussion is that eBrains started in 2018 with a 50 million grant, but apparently, I thought it was secured, but apparently, according to this article, the funding for the future is not secured, so there is a possibility for this to go into private or commercial funding, which obviously would be an interesting point for discussion if that was to be the case. And also, this is obviously just a feature article about the project and not the official review. So the European Commission will start its program review in November, and the results are going to be published in January next year, so 2024. But what these mega projects, these 10-year programs tend to do, ideally, is they create a community of scientists, and they also focus on common goals. So for everyone trying to set up a 10-year program, these are the things to consider. And I think this is also a nice project to learn from and see what to do, what not to do, what works, what doesn't work. And that's it. Happy to discuss. This is the part where you start talking. Valentina.
Hi, Steph. Thank you for the update. I was wondering, so some of the maps that you showed is basically a collection of already existing atlases, right? Of the white matter. What was the problem with cognition? I mean, there are available maps also that represent cognition, and we know it. So why did they give up with cognition?
Technically, they didn't give up. They did bring it back in. And obviously, in that very short feature article, it doesn't specify why they took out cognition in the first place. And I wasn't involved in the early days, so I wouldn't know the ins and outs. I can just tell you that we had a summit meeting in, May, March, some point earlier this year in Marseille. And it was amazing to see what they actually developed, what they came up with, the technology. It's genius. But do you know me? I'm cognitive clinical mainly. So I was sitting there, I was like, but where's the cognition? Where's the application for the individual patient? And they have the digital twin models and have fantastic results, but I was still a bit disappointed on the cognitive side. But that said, eBrains is a openly available platform, so maps can always be added. That's the beauty of it. You can just literally throw it in and build up the brain as we know it.
Okay, so this is like, it could be a good idea maybe to merge Leah's work and Leah's maps on the website.
It's very much work in progress at the moment. So yeah, and they're very open. So I talk to them a lot, especially about the tractography side of it. And they're very open to collaborate and have input.
Thanks.
Marcella or Chris, who of you had a question?
Yeah, so about the beginning of the project, I guess, because I think they came back to something that works better now. But I think what happened at the beginning, why it didn't work at the beginning and they had to restructure and all, I think it's symptomatic of a lot of research and research groups, because now research has to deal with technology, but sometimes with technology that they don't have experts in labs. I'm thinking about computer science, especially, and like developing like software development and all. I don't, well, yeah, I kind of know why labs don't want to hire actual professionals to develop apps, but also I think the main problem is organization, because developing an app or developing a massive program to simulate the brain or any other like big program, it needs a clear organization. And also people have to work together. At some point in your presentation, you were saying that they were making several projects that would come together at the end. And I think that is actually a mistake, because I can see that when because research is difficult, and it's also not what we expect at the beginning. I don't know any research project that went exactly to plan up to the end. So you always have to either change your objectives, lower them, or change them. It always moves. So if you work independently in the hope that in the end it's going to come together, I think it's going to be very difficult, and it might even fail, because you have to talk all the way through, not necessarily in great details, but you need to keep working together all the way through. Otherwise, I don't think it can work correctly. And I think that's why some of the results of these projects are a little bit underwhelming.
Very good point, and that is one of the things they also realized and changed. So the 6 lines were very much discipline specific, right? It was, what did I say, neuroprosthetics, algorithms, computing. Like, it was basically based on your academic background, whereas now they changed it to big questions. So it doesn't matter what your background is, but you try to solve the same common question, and I think that's a better
that makes more
approach
sense,
to it.
in my opinion.
But time will tell.
Yeah.
Neat.
Yeah, I'm skeptic that, if you're looking for integration or synergy within a group, I think it's becoming exponentially harder as a group is growing or like becoming bigger. And here we're talking about a lot of money and a lot of people that really need to work together to achieve their goal. It's very different from Human Connectome project, which has for purpose to map the connectome, but by acquiring data and making it available to the community. Here, like says, like work package of people that were supposed to work together to compress data, but and arrive to this final goal, which is a human brain simulation.
But there is ways of doing it. So, for example, the papers they write is quite a neat setup where a core team is drafting the paper, then it's circulated to a wider circle within the HBP, to the point where later on is posted online as a preprint, and everyone can feedback and input to it. So you could have a similar onion structure, so to speak, for project work. If it works for papers, why shouldn't it work for big questions?
I don't know if this, but that will be a hierarchical organization. So you have different modules that like work in a serial way. So the sum is not done, the whole is not more than the sum of the part. That's really what they try to do with this objective. I don't know. It's discussable. I see that they put a strategy, but that might not be the best to harvest most of the ideas and the people. I don't have a better idea.
But it's not only hierarchical, because you can have integration within each layer of the onion. You may not have the best integration across,
but not between.
layers.
Yeah. Not between. Well, it is what it is. I had a question concerning the digital twin. How many digital twins do they have?
Question, I don't know.
And how do they model intervention? Those digital twins.
There's I can link the papers in the how do you call it, video description later on. But they showed some of the results where they basically tried to get as much data as they could of a patient and then put it online, and then basically mapped things like functional connectivity, knocking out a hub to simulate brain surgery, and see how taking that hub out of the connectivity actually changes the functional connectivity. So great ideas, but to me it was still a bit like, I would not have a certain cut in my brain based on a digital twin model at this point.
But especially functional connectivity got a lot of partial effect. So if you have like two correlation within the same voxel, that will drop the overall level of correlation. And this is not for, I think.
Well, but the beauty of the multi-level is that you can integrate the levels and you can selectively knock out the structure, the functional connectivity. But again, bear in mind that the model can only be as good as the data you put in, and we've seen already some of the limitations here. But the idea is really that for the first time, you have all those levels from cellular, genetics, molecular, all the way to connectivity, where you can see the effect of changes. Annie.
Yeah, to maybe as a final question, I don't know if you have an answer to this, just more of a curiosity, what you think the effect of this will now be for funding in the future. As in, because before knowing what it was about, I knew about the name of it and that it was a little bit laughed about even, how little came out. So I'm wondering if that means that projects in the future of this size will not be funded like that anymore because of its reputation a little bit, or maybe if that's even a good thing since it seems to be so hard to govern of this size. But this is me never having worked with really, really big money and projects like that. But yeah, I was just wondering if you have a prognosis for the future.
Obviously, I'm not a funder, so I can't tell you how that affects the strategy. But things are coming out of the project, not necessarily what they had hoped to get out of it, but there is a legacy. I'm actually more worried about the funding of e-brains in that regard. So I think big projects, they have their place and their time, and they will probably receive funding, maybe not 600 million. But we need those 10-year projects. Science is not necessarily fast science, where you can do it fast, but sometimes you just need the time, especially when you work in the clinical setting. This data doesn't come quickly, like you need a couple of years to collect it anyways. So there is a place for big programs, and 10 years is a long time. People come and go. You need substantial funding to keep that going. So I don't think that this will be the death of big programs. But with eBrains, for example, if that is not funded by the European Commission going forward, but it will be funded with private and industry input, then I'd be a bit more worried about that, because then you move from a scientific-led initiative to a company, CEO, different priorities, different strategies, also different governance of the data, I guess, and especially the idea of everyone is just throwing in their data. Great idea. But, and you know this very well, we can't even get our patient data out of a building, let alone giving the data across a country border to a public online database. That to me, when it comes to clinical applications, is the biggest obstacle.
I also don't think they shouldn't be funded. I was just, with the governing behind it, I think it sounds like it was so distributed that it then was hard to come back together, right? And I'm sure there's ways to do this with even much bigger projects.
Yeah, there was a change in leadership, which definitely helped. Don't envy the person who took over, because this is a big project. But I think Katrin Ammons is doing a fantastic job in trying to rally up the troops behind her. There is other big projects funded by the European Commission, and they probably have a different structure in the way they're run, and they're not as open. So the HPP is really like for the entire community to figure out how the brain works, which arguably is too big of an aim and too many people involved in it. But there's other big projects that received substantial funding, and they're a bit more focused, for example, on autism or other aspects. So that might be the way to go. Have big questions where you combine people with different expertise, but working towards a common goal, and have specific targets. You want to get a bit more specific than how does the brain work? Any other questions? Points to consider? No, in that case, we're bang on time. Thank you so much for being back to Neuroccino. Next week, Lilith is going to present a very exciting paper. And as I said, if you want to come and present, this could be feature articles, actual research articles, reviews, book chapters, or any piece of exciting science you came across, just let us know and the floor is yours. Have an exciting week in science. See you soon. Bye.